Count in your head, slowly. 1, 2, 3, 4, and keep going, not out loud, just the sense of the numbers stretching away from you without any end. Now cross out every odd one. You have just thrown away half of everything you had. 1 is gone, 3 is gone, 5 is gone, on and on forever, and what is left ought to be far smaller than what you started with. So let us check. Set the two collections side by side. 1 against 2, then 2 against 4, then 3 against 6. Every number you began with gets exactly one partner. Every partner is used exactly once. And when you walk down the two lists as far as you can go, nothing is missing from either side. You threw away half and you lost nothing. You might reasonably decide that this is simply what infinity is. A place where size stops meaning anything, where all endless things are the same endless thing. And the sensible move is to stop asking. However, that turns out to be wrong. There is more than one size of infinity, and the proof of it is short enough to say out loud in under a minute, and it changed what mathematics was allowed to think about. Tonight we go slowly through all of it. A Greek runner who cannot finish a race, a hotel with no vacancies that always has room, a question that has been proved to have no answer, and a ball cut into pieces and put back together as two. You do not have to follow any of it. Fall asleep whenever you like. The numbers will keep going without you. Let's begin. Chapter 1. Begin with a race that nobody can finish. Invented about 2,500 years ago in a small Greek colony on the coast of southern Italy. The man who invented it was Zeno of Elea. We know very little about him. He was a student of Parmenides. He seems to have been born around 490 before the Common Era, and not one complete sentence of his writing has survived. Everything we have of him comes second-hand, mostly from Aristotle, who wrote his arguments down carefully in order to explain why they were wrong. Here is the one people remember. Achilles, the fastest runner in the world, races a tortoise. Because he is generous and because he is quick, he gives the tortoise a head start of, say, 100 paces. The gun goes. Achilles runs. To catch the tortoise, he must first reach the place where the tortoise began. That takes him a moment, and in that moment the tortoise has moved forward a little. Not far. It is a tortoise, but it has moved. So now Achilles must reach that new place. He does quickly, and in the time that takes, the tortoise has crept forward again. A smaller distance this time. Still, forward, and again, and again. Every time Achilles arrives at where the tortoise was, the tortoise is no longer there. The gap shrinks, it becomes tiny, it becomes almost nothing. But there is always another gap, because there is always another arrival and another small crawl. Zeno's conclusion is that Achilles never passes the tortoise. There are infinitely many of these catching up steps, and you cannot complete infinitely many of anything. Now, you know perfectly well that Achilles passes the tortoise. Anyone who has ever walked past a slow animal knows it. That is what makes the argument worth 2,500 years of attention. It is not asking you to believe something false about running. It is showing you that the way you describe motion contains something you cannot explain, and inviting you to find out what Zeno had others. In the one usually called the dichotomy, you do not even need a tortoise. To walk across your room, you must first get halfway. Before that, a quarter of the way. Before that, an eighth. Peel the journey backwards, and there is no first step, because whatever step you name, there is a smaller one that must come before it. So the walk cannot begin. Let your eyes close for this one if they want to. The argument works just as well in the dark in another. An arrow flies. At any single instant of its flight, the arrow occupies exactly one position, and in that instant it is not moving, because motion needs a stretch of time, and an instant has none. So at every instant, the arrow is at rest, a flight made entirely of moments of rest. Ancient writers counted somewhere around 40 of these arguments. 4 survive in any real detail, and the shape is always the same. Take something ordinary, break it into endlessly many pieces, show that the pieces will not go back together. What did the Greeks do with this? Aristotle, in the Physics, gave the answer that would hold for the next 2,000 years, and it is worth understanding, because it is genuinely clever rather than merely cautious. He said, there are 2 different things people mean by infinity, and they have been confusing them. The first he called potential. It means a process that has no natural stopping place. Whatever number you have counted to, you can count one higher. Whatever line you have drawn, you can extend it. Whatever piece you have, you can halve it. There is no last step, and that is fine, because at no moment are you ever holding an infinite thing. You are holding something finite, with more available. The second he called actual. This is the completed endless thing, not the counting, but all the numbers at once, gathered, finished, in your hand as a single object, not the halving, but the whole infinite collection of halves, existing all together. Aristotle allowed the first and forbade the second. Potential infinity, he said, is real and harmless. Actual infinity does not exist and cannot be reasoned about without producing exactly the sort of trouble Zeno had been producing. It was a ruling, and it stuck. For roughly 2,000 years, careful thinkers in Europe and around the Mediterranean worked with a rule that said, you may go on as long as you like, but you may never arrive. Mathematics was allowed to say that a sequence gets closer and closer to something. It was not allowed to say that it gets there and that the whole endless sequence is itself a thing. You can see the tidiness of it. If actual infinity does not exist, then Zeno's infinitely many steps are not a completed collection of steps that Achilles must somehow finish. They are just a way of describing the run that you happen to have chosen, and you could have chosen a different one. The paradox stops being about the world and becomes a remark about your bookkeeping. That is a good answer. It held for a very long time, and it held for a reason. But it is not the whole answer, and everyone knew it, because it leaves the arithmetic untouched. If you actually try to add up Zeno's shrinking distances, half the room, then a quarter, then an eighth, forever you are adding infinitely many positive numbers. Common sense says that adding forever gets you to forever, and the room is only 4 meters across, so something has to give. Either the walk really is impossible, which it plainly is not, or an endless list of positive numbers can add up to a perfectly ordinary total, which sounds like it cannot be true. It can. That is the next thing. For now, notice what Zeno actually did. He did not solve anything. He took the most familiar experience there is, crossing a room, and pointed out that nobody could say clearly how it worked. Then he waited, and the waiting lasted longer than most civilizations. There is something restful in that, I think. A problem sat unsolved for 2 millennia, and the world kept turning, arrows kept landing, tortoises kept losing races. Nothing bad happened because the explanation was missing. The runners ran anyway. Whatever you have not worked out today can wait like that too. It will still be there, patient and no worse for the delay. Chapter 2. So let us do the arithmetic that Zeno left lying there, because it is gentler than it sounds. You are crossing a room. First you go half of the way, then half of what is left, which is a quarter, then half of that, an eighth, then a 16th, a 32nd, a 64th, and onward without end. Add them as you go, and watch where the running total sits, 1/2, then 3/4, then 7/8, then 15/16, then 31/32. Say those aloud slowly, and you can hear what is happening. Each total is a little closer to one whole room, and each one falls short by exactly the size of the next piece. The gap is always there, and the gap is always halving. After 20 steps, you are within about 1/millionth of the far wall. After 40 steps, within about 1/millionth of a millionth. The total never exceeds 1. It never quite equals 1 at any finite stage, but there is no number smaller than 1 that it fails to pass, and that is the crucial thing. Name any target short of the wall, however close, and the running total goes past it. So 1 is the only number that fits as the destination, and mathematics says, sensibly, that the sum of all those pieces is 1, not approximately 1. 1. That single move is the resolution of Zeno, infinitely many steps, each taking a real amount of time, adding up to a perfectly ordinary, finite amount of time. The steps get small fast enough that the endlessness never gets a chance to accumulate into anything large. Achilles catches the tortoise at a specific moment, and you can work out exactly which moment and the infinity of catching up stages all happen inside it. Notice what had to be given up to say that. You had to be willing to talk about the whole endless collection of pieces at once and assign it a single value, which is precisely the thing Aristotle forbade. The answer was sitting on the far side of his fence the entire time. Here is where it gets more interesting and more careful. Not every endless sum settles down like that. Take the numbers 1, then 1/2, then 1/3, then 1/4, then 1/5, going on forever. Each term is smaller than the last. They shrink to nothing. If shrinking were enough, this ought to add up to something modest. It does not. That sum grows without any limit at all. Go far enough, and it passes 10, then 100, then 1,000,000. It takes an absurd number of terms to do it, but it gets there, and it keeps going, and nothing stops it, ever. This was proved around 1350 by a French bishop and scholar named Nicole Oresme, and his argument is so clean you can hold it in your head. Group the terms. Take 1/2 by itself. That is at least a half. Take the next 2, a 1/3 and a 1/4, and notice that each is at least a quarter, so together they are at least a half. Take the next 4, a fifth through an eighth, each at least an eighth, so together at least a half. Then the next 8 terms give at least a half. Then the next 16. Every group you form is worth at least a half, and there are endlessly many groups. So the total is at least a half added to itself forever, which has no ceiling. That result is worth resting on. 2 endless sums, both made of terms that shrink to nothing, and one arrives at a tidy destination, while the other wanders off past every number you could name. Shrinking is not enough. It matters how fast. Let yourself drift here if you would like. This part will be waiting when you come back, and it does not mind being missed. Long before Oresme, someone had already been doing this properly. Archimedes of Syracuse in the 3rd century, before the Common Era, worked out the exact area enclosed by a curved parabola using what is now called the method of exhaustion. He filled the shape with triangles. One big one, then smaller ones in the gaps, then smaller ones in the gaps left by those forever. Each round added a quarter as much area as the round before, and he showed the whole thing comes to 4/3 of the first triangle. He was adding an infinite series and getting the right answer, roughly 1800 years before calculus existed. But he would not say it that way. He proved it by showing that the area could be neither greater nor less than 4/3, so it had to be exactly that, which let him avoid ever claiming to have completed an endless sum. He respected the fence even while reaching over it. There is a lovely postscript. In 1906, a Danish scholar named Johann Ludwig Heiberg examined a prayer book in Constantinople and found that the parchment had been scraped and reused. Underneath the prayers was a copy of a lost work by Archimedes, now called The Method, in which he explains how he actually found his results before dressing them up in rigorous proof. He was weighing shapes against each other, slice by slice, treating areas as though built from endlessly many lines. The private working was far bolder than the published version. Now the caution, because it is the honest part of tonight. Once you allow yourself to add endlessly many things, you have to be careful in ways that ordinary arithmetic never demanded. Around 1703, an Italian monk and mathematician named Guido Grandi looked at a very simple series. 1 minus 1 plus 1 minus 1 forever. Group it one way, pairing the first with the second and the third with the fourth, and every pair cancels, so the total is 0. Group it the other way, leaving the first one alone and pairing everything after it, and everything after cancels, so the total is 1. The same list of terms, 2 different answers, and the only difference is where you put the brackets. Grandi's series does not have a sum in the ordinary sense. It never settles. It flips between 1 and 0 forever, and the correct thing to say is that it has no total at all. It gets stranger, and Bernhard Riemann proved how much stranger in the 19th century. Take a series that does settle, but only because of cancellation between positive and negative terms. 1 minus 1/2 plus 1/3 minus 1/4, and so on. That one genuinely converges, but Riemann showed that by reordering the terms, Using every term exactly once and never leaving any out, you can make it add up to any number you choose in advance. 7, 0, minus 1,000, whatever you like, the same terms, the same infinitely many of them, rearranged, giving a different answer. In finite arithmetic, order never matters. Here it does. So the tool that dissolved Zeno's paradox has an edge to it. Endless sums are real and usable, and they answer the oldest puzzle in the subject, and they will not tolerate being handled the way you handle 3 plus 4. That is the pattern for the whole night, really. Infinity is not unruly. It simply has its own rules, and they are not the ones you learned first. The room can be crossed. Take a slow breath. You are already on the other side of it. Chapter 3. In 1638, an old man under house arrest in a villa outside Florence published a book he was not allowed to publish. Galileo Galilei was 74. He had been convicted 6 years earlier, forbidden to print anything further, and confined to his house at Arcatri for the rest of his life. He was going blind, and he spent those years writing the book that many people consider his best, a set of dialogues on motion and on the strength of materials, which was smuggled out of Italy and printed in Leiden in the Netherlands, safely beyond the reach of the people who had silenced him. Tucked inside it, on the way to other business, is a short conversation about counting that stops in a very particular place. The speaker, Salviati, invites you to think about the whole numbers. 1, 2, 3, 4, and so on. Then he asks you to think about the squares. 1, 4, 9, 16, 25, 36. Now, he says, look at how thin the squares become. Among the first 10 numbers, there are 3 squares. That is a healthy share. Among the first 100, there are 10. Among the first 10,000, only 100. Go up to 1,000,000 and the squares are down to 1 in 1,000. Keep going and they thin out toward nothing. Almost every number you meet is not a square, and the further you walk, the more true that becomes. So there are obviously fewer squares than numbers. It is not close. The squares are a vanishing sliver of the whole. Then Salviati says the other thing. Every whole number has exactly 1 square. 1 goes with 1, 2 goes with 4, 3 goes with 9, 4 goes with 16. And every square has exactly 1 root, so nothing on that side is left over either. Pair them off, and the pairing is perfect. No number lacks a square, no square lacks a number, and nothing is doubled up or stranded, so there are exactly as many squares as there are numbers. Both arguments are correct. That is the whole difficulty. One says the squares are a shrinking sliver. The other says the squares match the numbers exactly, 1 for 1, with no remainder anywhere. And they are talking about the same 2 collections. You may recognize this. It is what you did in the first minute of tonight with the even numbers. Galileo found it 400 years ago, wrote it down plainly, and understood exactly how uncomfortable it was. Here is what he concluded. He decided that the words we use for size simply do not apply. Equal, greater, less. Those words work for finite quantities, he said, and they lose their meaning when carried across to infinite ones. You may not say that there are more numbers than squares, and you may not say there are equally many, because neither statement means anything. The question is malformed. That is not a shrug. It is a genuine philosophical position, and for a long time it was the respectable one. If two perfectly sound arguments about the same objects give opposite answers, the reasonable diagnosis is that the question itself is broken, not that one of the arguments is wrong. Ret here for a moment, if you like. Nothing in the next few sentences depends on you following the last few, and yet, look again at the two arguments and notice that they are not answering the same question. They only sound as if they are. The first argument is about density. It asks what fraction of the numbers up to some point are squares, and the honest answer is that the fraction shrinks toward nothing. That is a true and useful fact, and it says something about how the squares are distributed along the line. The second argument is about pairing. It asks whether the two collections can be matched up without leftovers, and the honest answer is that they can. That is also true, and it says something about the collections taken whole. For finite collections, those two questions always agree. If you have a bag of buttons and a bag of coins, and you can pair them off perfectly, then they are the same size by any measure you choose, and no notion of density can disagree. The two ideas march together so faithfully in ordinary life that we never notice they were ever two ideas. Infinity pulls them apart, and when they come apart, you have a choice about which one deserves to be called size. Galileo declined to choose. He looked at the split and decided that neither branch could carry the word, so the word had to be set down. It is worth saying that he was not being timid. He was working within Aristotle's framework, in which a completed infinite collection is not a legitimate object in the first place. If the whole collection of numbers is not a thing you can hold, then asking how big it is, compared to another thing you cannot hold, is not a question with an answer. Given his premises, his conclusion follows. He was also not the first to notice. Similar observations turn up in the medieval period. Various scholars had remarked that two concentric circles, one small and one large, have exactly as many points as each other, since you can run a straight line out from the center and hit each circle exactly once, pairing every point on the inner circle with one point on the outer. The small circle is shorter. The points match anyway. That puzzle was known and discussed, and it was always filed under the same heading, which was that infinity is where reasoning stops behaving. So, the door was found repeatedly over several centuries, and every time someone reached the handle and decided not to turn it. 250 years after Galileo's book, someone did turn it, and the move was almost absurdly simple. He kept the pairing argument and threw away the objection. He said, in effect, that if two collections can be matched one against one with nothing left over, then we will call them the same size. Not because it is obvious, because it is the definition chosen deliberately, and we will follow it wherever it goes, including to the strange places, including to the squares having as many members as the numbers they came from. It sounds like giving up. It sounds like renaming the problem so that it stops being a problem. It is not, and the reason it is not is what the rest of tonight is about. Because once you accept that definition and start applying it, it does not flatten everything into one gray sameness. It starts making distinctions. It says that some infinite collections match, and others provably cannot, no matter how you try to pair them. The definition that looked like surrender turns out to have teeth, and it cuts the infinite into layers. Galileo did not live to see any of that. He died in 1642, still confined, 4 years after the book came out. The conversation about the squares sits in the middle of a treatise about falling bodies and beams, almost as an aside. The way a person mentions something odd they noticed and then moves on. There is no hurry in any of this. He waited, without knowing he was waiting. The answer arrived long after, and it was worth the interval. Let your breathing slow. The squares are still out there, thinning out, matching perfectly, doing both at once, entirely at peace about it. Chapter 4. Before the Mathematics. A shepherd, imagine you keep sheep, and you cannot count. Not because you are foolish, but because you live long before anyone invented a word for 17. You still need to know, every evening, whether all your sheep came home. So, in the morning, as they file out of the pen, you drop 1 pebble into a pouch for each animal that passes. 1 sheep, 1 pebble. You do not know how many pebbles that is, and you do not need to. In the evening, as they file back in, you take 1 pebble out for each animal returning. If the pouch empties exactly as the last sheep walks in, everything is well. If pebbles are left, something is missing, and you go out looking. That shepherd is doing something more fundamental than counting. He is comparing 2 collections without ever measuring either one. He is asking whether they can be paired off perfectly. The answer to that question does not require numbers at all, and it works on collections far too large to count, which means it also works on collections that cannot be counted in any ordinary sense. And that is the crack through which the whole subject opens. The man who walked through it was Georg Cantor, born in St. Petersburg in 1845, to a family that moved to Germany when he was a boy. He spent most of his working life at the university in Halle, a decent but modest institution, never quite reaching the prestigious post in Berlin that he wanted. He was a careful, religious, somewhat solitary man who came to this question sideways, through a technical problem about how functions can be represented by waves, and then could not put it down. His decision was the one Galileo Galilei declined to make. 2 collections are the same size, Cantor said, when their members can be paired off 1 against 1, with nothing left over on either side. That is the definition, not a comparison of density, not an intuition about which one looks bigger, just the pairing. Follow that definition honestly, and you have to accept some things. You have to accept that the even numbers are the same size as all the numbers, because of the pairing you did at the very start of tonight. You have to accept that the squares are the same size as the numbers, exactly as Galileo showed. You have to accept that if you take the whole numbers and throw away the first million of them, what remains is still the same size as what you began with, because you can pair each survivor against a number in the original list without running out. None of that is a contradiction. It is only a surprise. A collection can be paired perfectly against a part of itself. That never happens with anything finite, and it always happens with anything infinite. And eventually someone realized this could be turned into the definition of infinite rather than a scandal about it. David Hilbert, one of the great mathematicians of the following generation, found the friendliest way to say all of this. He described it in a lecture in the 1920s, and it traveled far beyond mathematics after the physicist George Gamow put it in a popular book in 1947. Picture a hotel with rooms numbered 1, 2, 3, and so on forever. There is no last room, and every room is occupied. The night manager has a full house. A traveler arrives and asks for a room. In an ordinary hotel, that is the end of the conversation. Here, the manager makes an announcement. Every guest is to pack up, step into the corridor, and move into the room whose number is 1 higher than the room they are in. The guest in room 1 goes to room 2. Room 2 goes to room 3. Room 3 goes to room 4. Every guest has somewhere to go, because for any room number, there is always a next one. Nobody is pushed off the end, because there is no end. And when the shuffling stops, room 1 is empty. The traveler checks in. The hotel was full, and it was not full. And both of those statements are correct at the same time, because full means something different when there is no last room. Let that be a bedtime image rather than a problem. You do not have to hold it. It will still be true in the morning. Now a coach pulls up outside, carrying infinitely many travelers, one for every whole number. Coach passenger 1, coach passenger 2, and so on without end. The manager is unbothered. This time, the announcement is that every guest should move to the room whose number is double their current one. Room 1 goes to room 2. Room 2 goes to room 4. Room 3 goes to room 6. Room 17 goes to room 34. Every existing guest lands somewhere. Nobody collides with anybody. And now every odd-numbered room stands empty. There are infinitely many odd rooms. The coach empties into them. Passenger 1 into room 1. Passenger 2 into room 3. Passenger 3 into room 5, and every traveler sleeps indoors. The hotel that was already full has just absorbed as many new guests as it had guests to begin with, and it is full again in exactly the same way. There is a version where infinitely many coaches arrive, each carrying infinitely many passengers, and the manager handles that too, though it takes a cleverer scheme, and we will build that scheme properly in a little while. What the hotel is really showing you is an arithmetic that has quietly stopped behaving. The size of the whole numbers added to 1 gives the size of the whole numbers. Added to itself, it gives the size of the whole numbers. Doubled, halved, stripped of 1,000,000 members, it does not move. In ordinary arithmetic, adding something changes the total. Here it does not, and the reason is not vagueness or sloppiness. It follows exactly and provably from the pairing definition, and you can write out the pairings by hand. Cantor gave this particular size a name. Any collection whose members can be paired off against the whole numbers is called countable, and the point of the word is that you could, in principle, arrange the whole collection into a single endless list. First one, second one, third one, and so on, such that everything in the collection appears somewhere in the list, at some definite position. That is all countable means. Not that you could finish counting, only that there is a place in line for everything and nothing gets left off the list. So here is the state of things at the end of this stretch of the night. There is a size, the size of the whole numbers. It is remarkably absorbent. You can add to it, double it, thin it out, and it stays where it is, which raises the obvious question. And it is the question the rest of the night turns on. Is that just what infinity is? One single size, endlessly forgiving, swallowing everything you hand it? We will spend the next stretch handing it larger and larger things and watching it swallow them, and then we will hand it one thing that it cannot. For now, the hotel has a room for everyone. The lights along the corridor go on forever, and every door is closed and quiet. Chapter 5. So we start handing it larger things. The whole numbers are spread out. 1, 2, 3, with clear gaps between them, nothing in between, each one standing alone, with room on either side. It is easy to believe that such a tidy, spaced-out collection could be listed. The fractions are not like that at all. Between 1 and 2, there is 1.5. Between 1 and 1.5, there is 1 1/4. Between those two, there is another. And between any two fractions you name, however close together, there are infinitely many more. Not a few. Infinitely many, every time. Forever, all the way down. Mathematicians call this being dense. There are no gaps anywhere. Pick any point on the line and any distance, however small, and there are endlessly many fractions within that distance of your point. So, the fractions look overwhelmingly more numerous than the whole numbers. The whole numbers are a scattering of fence posts. The fractions are a fog, filling every space between them. They are the same size. Cantors' way of showing it is one of those arguments that seems like a trick the first time, and like the only sensible thing the second time. Lay the fractions out in a grid. Along the top row, put everything with 1 on the bottom. So 1/1, 2/1, 3/1, 4/1. In the second row, everything with 2 on the bottom. So 1/2, 2/2, 3/2. Third row, everything over 3. And so on downward, forever. A grid endless in both directions. Every positive fraction is somewhere in that grid. Whatever fraction you name, it sits at a definite place determined by its top and bottom. Now the question is how to walk through the grid so as to reach everything. You cannot go along the first row because the first row never ends and you would never start the second. You cannot go down the first column for the same reason. Any straight path gets trapped in one endless line and misses the rest of the grid entirely. So you go diagonally, start at the top left corner. Then take the 2 entries where the row and column numbers add to 3. Then the 3 entries where they add to 4. Then the 4 entries where they add to 5. Each of those diagonal stripes is finite, containing only a handful of entries, so you can always finish one and move to the next. Walk the stripes in order, and you sweep the entire grid. Every single entry gets visited at a definite step after finitely many others. Nothing is missed, and nothing waits forever. Skip the repeats as you go, since 2/4 is the same number as 1 over 2 and does not need a second place in line. What is left is a genuine list of the fractions. First one, second one, third one. On and on, with every fraction appearing at some definite position, which means the fractions are countable. Paired off one for one against the whole numbers with nothing left over. All that density, all that fog, and it fits into the same size as the fence posts. Notice how the trick works, because it comes back later. The fractions are two-dimensional in a sense, being made of a top and a bottom, and the diagonal walk is a way of flattening two endless directions into one endless line. That same maneuver handles Hilbert's infinitely many coaches, each carrying infinitely many passengers. Number each coach, number each seat, arrange the passengers in a grid, walk the diagonals, and everyone is assigned a room. Let your attention wander off here if it likes. The walk continues on its own, stripe by stripe, patient as anything. Cantor then handed infinity something considerably heavier. Consider not just fractions, but every number that solves some ordinary equation built from whole numbers. The square root of 2 solves the equation, saying that a number times itself is 2. The cube root of 5 solves its own. There are far more elaborate examples. Solutions of long equations with many terms, numbers whose decimal expansions never repeat and never end. These are called the algebraic numbers, and they include every fraction, and a great deal besides. In 1874, Cantor proved that this collection is also countable. The idea is to organize the equations rather than the numbers. Each equation is built from a finite pile of whole numbers, so you can assign it a size made from its degree and how large its coefficients are. For any given size, there are only finitely many equations, and each equation has only finitely many solutions. So, you list all the equations of the smallest size and write down their solutions, then move to the next size and the next. Every algebraic number turns up somewhere in that list at some finite position because it belongs to some equation, and that equation has some size, and that size comes up eventually. So the square root of 2 has a seat. So does the 7th root of 13. So does every solution of every whole number equation anyone will ever write down. All of them fit into the same size as 1, 2, 3, and here the same paper does something that ought to feel impossible. Cantor also proved, in that very same year, that the numbers on the line as a whole are not countable. We will build that argument slowly in a moment, but hold the consequence for now, because it arrives before the proof does, and it is beautiful. If every algebraic number fits into a list, and the numbers on the line do not fit into a list, then there must be numbers on the line that are not algebraic, numbers that solve no whole number equation at all. They are called transcendental, and not a few of them. Since the algebraic numbers are countable, and the whole line is not, the transcendental numbers must make up essentially all of the line. The ones we can pin down with equations are the rare exceptions, a thin dust scattered through an ocean of numbers that no equation reaches. Before that argument, transcendental numbers were hard to come by. Joseph Liouville had constructed one deliberately in 1844, building it digit by digit specifically so that no equation could catch it. Charles Hermite proved in 1873 that the base of natural logarithms is transcendental, and it took real work. Ferdinand von Lindemann proved in 1882 that the ratio of a circle's circumference to its diameter is transcendental too, which settled a question the Greeks had asked, showing once and for all that you cannot square the circle with compass and straight edge. Each of those was a serious achievement, one number at a time. And Cantors' argument said, without exhibiting a single example, that almost every number is like that. He proved the crowd exists without ever pointing at one of its members. Some mathematicians found this unsatisfying to the point of objectionable, and their objection is not silly. There is a real difference between showing that something exists and being able to hand it to someone. But the counting was correct, so the running score at this point in the night is that infinity has absorbed everything offered to it. Add 1. It does not notice. Add a copy of itself, unchanged. Fill every gap with a fog of fractions, still countable. Throw in every solution of every equation, still countable. It begins to feel like nothing could ever be too big. Something is, and it has been lying in plain view the whole time. In the short stretch of the line between no rush to get there, that stretch has been sitting quietly since before anyone thought to look at it, holding more than anyone expected, asking nothing of anybody. Chapter 6. Take the stretch of line between 0 and 1 and think about every number that lives on it, not just the fractions, every number, everything you could write as a decimal point, followed by an endless string of digits. Some of those strings settle into a repeating pattern, and those are the fractions. Some never repeat at all, wandering forever without a rule, and those are the rest. The claim is that this collection cannot be put into a list, not that it is hard, not that nobody has managed it yet, that no such list can exist, and we can see why. In about 2 minutes, here is the shape of the argument. Suppose somebody hands you a list claiming it contains every number between 0 and 1, first number, second number, third number, going on forever, and they promise that nothing has been left off. You do not need to know what their list looks like. You do not need to know how they built it. You are going to construct, from their own list, a number they have missed. You do it 1 digit at a time. Look at the first number on their list, and look at its first digit after the point. Whatever that digit is, choose a different one for your number's first digit. If theirs is a 5, write a 6. If theirs is anything else, write a 5. The rule does not matter as long as you differ. Now look at the second number on their list, and at its second digit. Choose something different for your second digit. Then the third number's third digit. Choose differently. Then the fourth number's fourth digit, and the fifth number's fifth digit, and onward down the diagonal of their list, forever, always disagreeing with whatever you find. When you are done, you are holding a number between 0 and 1. It has a first digit, a second digit, a third digit, all the way along, and it is a perfectly legitimate decimal. Now ask where it sits on their list. It is not the first entry, because it differs from the first entry in the first digit. It is not the second entry, because it differs there in the second digit. It is not the 94th entry because it differs from that one in the 94th digit. Whatever position you propose, your number disagrees with the occupant of that position at exactly that place by construction. So it is not on the list anywhere, but their list was supposed to contain every number between 0 and 1, and here is a number between 0 and 1 that is not on it. The promise is broken. And here is the part that matters. This is not a flaw in their particular list that a more careful person could fix. Whatever list anyone produces, this same procedure runs down its diagonal and builds a number it missed. Every list fails, and every list fails in the same way, and there is no repair, because the repair itself is just another list with its own diagonal, therefore no list of all the real numbers between 0 and 1 exists. That is the diagonal argument. Georg Cantor published it in 1891. He had already proved the result by a different and more laborious route in 1874 using shrinking nested intervals. But the diagonal is the version that fits on a page and that anyone can follow. Sit with the conclusion rather than the mechanics. The whole numbers can be listed by definition. The fractions can be listed by walking a grid diagonally. Every solution of every whole number equation can be listed by sorting the equations by size. All of those collections are the same size, the size called countable. The numbers on a short piece of line cannot be listed at all. They are strictly more numerous, not larger in some vague poetic sense. Larger in the exact sense that any attempt to pair them off against the whole numbers must leave some of them out. Provably, every time, there is more than one infinity. That sentence had not been available to anyone before. For 2,000 years, from Aristotle through Galileo Galilei, the standard position had been either that completed infinities do not exist, or that they cannot be compared. Now, there was a proof that they exist in different sizes, and that the difference can be demonstrated in a few lines. Let that settle at whatever pace suits you. You are not required to be awake for the consequences. Notice, too, that the argument has the same flavor as the shepherd with the pebbles. Nobody counted anything. Nobody measured either collection. The whole thing turns on whether a pairing can be completed without leftovers, and the answer is that it cannot, and the proof is a recipe for producing a leftover from any pairing you are offered. There is something else worth noticing, which is that the diagonal number is genuinely constructed. Hand over a list and the recipe hands back a specific missing number, digit by digit. This is not an abstract impossibility argument that leaves you empty-handed. It is a machine for building the exception. The reception was not simple. Leopold Kronecker had taught Cantor in Berlin and was one of the most influential mathematicians in Germany. He held a view that had real intellectual weight behind it, which was that mathematics should concern itself with objects you can actually construct in finitely many steps from the whole numbers. Completed infinite collections, sizes of infinities, numbers proved to exist without ever being exhibited. All of this struck him as not merely wrong, but as not being mathematics. He said so at length over years. He worked against Cantors' papers and against Cantors' career. The position in Berlin never came. Cantor was also unwell. From 1884 onward, he suffered repeated episodes of severe depression and spent long stretches in a sanatorium in Halle. It is tempting to draw a straight line from the opposition to the illness, and popular accounts often do, but that line is not something anyone can honestly establish. Depression of that kind does not require an external cause, and it visited him through periods of professional success, as well as periods of hostility. What is fair to say is that he was doing difficult, unpopular work under sustained criticism from someone he had once looked up to, and that he found it hard. He also had defenders. Richard Dedekind corresponded with him closely for years and understood immediately what he had done. Others came around more slowly, and within a generation the whole of mathematics had been rebuilt on the foundation Cantor laid, with sets underneath everything. But that is later. Right now, at the moment the diagonal argument lands, all that exists is a short piece of reasoning and a new fact about the world. There are at least two different sizes of endlessness, the size of counting and the size of the line. And they are not the same, and no amount of cleverness will make them match, which invites the next question quietly, without pressing. If there are two, are there three? Is there a largest, or does the latter keep going? The line between 0 and 1 is holding all of that already, and has been all along, taking up almost no space at all. Nothing about it has changed tonight except what you know. Chapter 7. Let us slow down before climbing. The last stretch did something quite large in a small space. So here is the whole of it. Again unhurried, with nothing new in it. Two collections are the same size when their members pair off with nothing left over. That is the definition, chosen on purpose. By that definition, the whole numbers, the even numbers, the squares, the fractions, and every solution of every whole number equation are all the same size, which we call countable, meaning they can be arranged into a single, endless list. The numbers on a short piece of line cannot be arranged into any list at all, because from any proposed list you can build a missing number by walking down its diagonal and disagreeing with every digit you pass. That is it. That is everything so far. If you have that, you have the difficult part of the night behind you. Now, gently, upward, the question is whether the ladder goes on. Two sizes are established. So is the second one, the top. To answer it, we need one more idea, and it is an idea you already use constantly, without a name for it. Given any collection, you can form a new collection whose members are all the possible selections you could make from the first one. Every way of choosing some of the things, including choosing all of them, and including choosing none, tray it with something small. Suppose you have 3 objects on a table, a spoon, a stone, and a leaf. How many different selections can you make? You could take nothing. You could take just the spoon, just the stone, or just the leaf. You could take the spoon and the stone, the spoon and the leaf, or the stone and the leaf. Or you could take all 3. That is 8 possibilities from 3 objects. With 4 objects, it would be 16. With 5, 32. Each new object doubles the count because every selection you already had now comes in two versions, one with the new object and one without. So, for finite collections, the selections always outnumber the members, and they do so dramatically. 10 objects give more than 1,000 selections. 20 objects give more than 1,000,000. The question is what happens when the original collection is endless. Take the whole numbers, all of them, and consider every possible selection you could make from them. The selection consisting of the even numbers, the selection consisting of the prime numbers, the selection consisting of just the number 7, the selection consisting of all numbers except 3, 11, and 40. Every conceivable choice, including infinitely many wild and patternless ones. Cantor proved that this new collection is strictly larger than the whole numbers, not the same size, larger in the exact pairing sense, provably, and the proof is the diagonal again, wearing a different coat. Suppose someone claims to have paired every whole number with a selection, so that number 1 has its selection, number 2 has its selection, and every selection appears somewhere. You build a selection they missed, like this. Go through the numbers one at a time. For the number 1, look at the selection paired with it and ask whether 1 is inside that selection. If it is, leave 1 out of your new selection. If it is not, put 1 in. Then do the same for 2 and 3 and every number after that, always doing the opposite of what you find. Your new selection now disagrees with every selection on their list because it disagrees with the first one about the number 1, with the second one about the number 2, and with the 100th one about the number 100. So it is not on their list, and their list was supposed to be complete, the same move. Walk down the diagonal, disagree with everything you pass, and you have built the exception. Wet your eyes now if they are ready. The ladder does not need watching. Here is why that result is the important one, more important in the long run than the line between 0 and 1. It does not mention numbers at all. The argument works for any collection whatsoever. Whatever you start with, the collection of its possible selections is strictly larger. So start with the whole numbers and you get something bigger. Now take that bigger thing and form all of its selections, and you get something bigger still, and again there is no top. There cannot be, because whatever you claim is the largest, the same argument immediately produces something larger from it. The ladder of infinities goes up forever, and each rung is strictly, provably, above the one below. That is a genuinely startling thing to have proved. And it took nothing more than the pairing definition, and one repeated trick. Cantor gave the sizes names. The smallest infinite size, the size of the whole numbers, he called Aleph Null, using the first letter of the Hebrew alphabet with a subscript meaning 0th. Above it sits Aleph 1, then Aleph 2, and onward through the Alephs. The size of the numbers on the line he called the Continuum, from the Latin for something unbroken. Now, a caution, because tonight is meant to be honest. None of this is a claim about things you could put in a room. Nobody is saying that there exist physically distinct quantities of stuff at each rung. These are statements about sets, which are mathematical objects. and the latter is a fact about the internal logic of collections and pairings. Whether anything in the physical universe corresponds even to the first rung is a separate question that we will come to before the night is out, and the answer is less confident than you might expect. There is a second caution. The names suggest a tidier picture than the mathematics actually delivers. Writing Aleph null, then Aleph 1, then Aleph 2 makes it sound as though we have a list of all the infinities in order, each one the next after the last. We have that for the Alephs. What we do not have from anything said so far is any idea of where the continuum sits among them. Is the size of the line equal to Aleph 1, the very next size up from countable? Or does it sit higher with other infinities in between? Cantor believed he knew the answer. He was certain the line is the next size up with nothing between, and he spent decades trying to prove it. He would go through periods of announcing he had it, then finding the flaw, then trying the opposite, then finding the flaw in that. The reason he never managed is not that he was not clever enough. The reason is stranger and quieter than that, and it took 2 more mathematicians and most of the 20th century to uncover. For tonight, though, the latter is enough. It rises without a top, each rung resting steadily on the one below, and it has been standing there in perfect order since long before anyone described it. Chapter 8. There is a second kind of infinite number, and almost nobody is told about it, and it is the more playful of the two. So far, every question has been how many whole numbers, how many fractions, how many points on a line. That is the counting question, and the answer is a size. The other question is in what order. For finite things, these 2 questions barely come apart. Line up 5 stones and you have 5 stones. And it does not matter which one you put first. Rearrange them however you like, and you still have a line of 5, indistinguishable in shape from any other line of 5. Now line up endlessly many. Put the whole numbers in their usual order. 1, then 2, then 3, going on forever. There is a first item. Every item has an immediate next one. And there is no last item. That arrangement has a name. It is called omega, the last letter of the Greek alphabet, and it is the first of the infinite ordinal numbers. Here is what makes it interesting. Take that same endless queue and add 1 more person, standing not at the front and not anywhere in the middle, but past the whole thing, behind everybody. There is no one immediately in front of them, because for any person in the queue, there is always somebody further back. So nobody is last before the newcomer. They simply stand beyond the end of a thing that has no end. You now have a different arraignment. It has the same number of people, since you can pair the new queue against the old one perfectly. But its shape is not the same, because this one has a last person, and the old one did not. That distinction is real, and you can point at it. That arrangement is called omega plus 1. Add another straggler behind that one, and you have omega plus 2. Keep going, and you have omega plus 3, and so on. And then, past all of those, you can put a whole second endless queue, in which case you have 2 complete copies of the whole numbers laid end to end, which is called omega plus omega. Nothing about this changes how many people there are. The counting answer stays exactly what it was, countable, aleph null, the same as it ever was. Only the shape changes. Let your thoughts settle into that Q if they want to. It is a peaceful place, and it stretches a long way. Now the part that surprises people who like arithmetic. Order matters in a way it never did before. Put one extra person at the back of the endless queue, and you get something new, omega plus 1, with a genuine last member. Put one extra person at the front instead, and nothing has happened at all. You still have a first person, then a second, then a third, forever with no last member. Give everyone new numbers, and it is identical in shape to what you started with. One placed before omega gives you omega back. One placed after omega gives you something strictly longer. So the order of addition changes the answer. That is not sloppiness or a definitional dodge. It is the direct consequence of what these objects are, which are shapes of arrangement rather than quantities of stuff. Multiplication behaves the same way. Two copies of the endless queue laid end to end is a longer shape than the queue itself. But replacing each member of the endless queue by a pair of people so that the queue becomes twice as crowded without ever ending gives you nothing new. Doubling in one direction lengthens. Doubling in the other does not. Cantor built all of this in the 1880s alongside the sizes, and he regarded the ordinals as the more fundamental of the two ideas. They are how you keep counting after the whole numbers run out, and they extend far past anything we have described. Past omega plus omega there is omega times omega, and past that a tower of omegas, and past that shapes with names that mathematicians had to invent notations. For because ordinary language runs out long before the ordinals do, and every single one we have mentioned is still countable, that is the thing to hold. All these ever longer arrangements, each provably a different shape from the last, and you could pair the members of any of them against the whole numbers with nothing left over. They are all the same size. They are simply different ways of laying that size out. Eventually, though, the shapes get so long that they can no longer be countable. Gather together every possible countable arrangement, all of them, and the result is an arrangement that is not countable itself. It is called the first uncountable ordinal, and it is the shortest possible queue that cannot be paired against the whole numbers. There is a strange and lovely detail about it. Stand anywhere inside that queue, at any position at all, and look back at everything before you. What you see behind you is always countable, always something you could, in principle, list. It is only the whole thing. Taken together, that is not. Every part of it is small. The totality is not. You may reasonably wonder what any of this is for. It turns out to be useful in a specific way. Ordinals measure how long a process can run before it stops. If you have a procedure that keeps reducing something, and you can show that each step moves you down the ordinals, then the procedure has to terminate eventually, because you cannot descend forever through them. There are results in logic about which procedures halt, and about the strength of different systems of proof that are stated in exactly this language. There are also puzzles, and one of them is charming. A creature has many heads. Each time you cut one off, it grows a great many more, and the number it grows increases explosively with every cut. It looks hopeless, but if you assign an ordinal to the creature's current state, that ordinal goes down with every cut, no matter how many heads sprout. And since you cannot descend forever, the creature always dies. Always. However badly it seems to be going, which is a nice thought to carry into sleep, actually. A thing that looks like it is growing beyond control, quietly and provably shrinking the whole time, on a scale that only shows up if you know where to look. The queue is long, tonight, and orderly, and everyone in it is exactly where they belong. Chapter 9. Now, the question Cantor could not answer, and the reason no one else could either. It is easy to state. There is the size of the whole numbers, the countable size, the smallest infinity there is, and there is the size of the numbers on the line, which the diagonal argument showed is strictly bigger. Is there anything in between? Could there be a collection too large to be listed, and yet too small to be paired against the line? Something sitting in the gap? Georg Cantor was convinced there is nothing in the gap. He believed the line is the very next size up from countable, with no room underneath it, and this belief is called the Continuum hypothesis. He tried to prove it for the better part of 30 years. The attempts have a rhythm to them that is painful to read about. He would find an argument become certain, write to Richard Dedekind or to others announcing the result. Then the flaw would surface. Then he would try to prove the opposite, that there is something in between and get somewhere, and then that would collapse as well. In one stretch, he swung between the two positions within a matter of days. He was also ill during much of it, in and out of the sanatorium at Halle, and by the later years his attention had turned partly to other things, including a long and unpersuasive effort to show that the plays of William Shakespeare were written by Francis Bacon. That detail is usually told as a sad joke. It reads differently if you think of it as a man looking for a problem he might actually be able to finish. When David Hilbert stood up in Paris in 1900 and set out the problems he thought should occupy mathematics in the coming century, the continuum hypothesis was first on the list. Not third, not seventh. First, that is how central it looked. A question about the two most basic infinite collections there are, and nobody could touch it. The resolution came in two halves, 30 years apart, and it is not the kind of resolution anyone expected. The first half came from Kurt Gödel, the Austrian logician who had already shown, in 1931, that any sufficiently rich system of mathematics contains true statements it cannot prove. In 1938, he turned to the continuum hypothesis and proved something careful. He showed that if the standard axioms of set theory are consistent, then adding the continuum hypothesis to them keeps them consistent. In other words, the axioms can never be used to disprove it. He did this by constructing a particular restricted universe of sets, a lean one containing only what the axioms force into existence, and demonstrating that inside that universe, the hypothesis holds. So, the continuum hypothesis could not be refuted, which sounded at the time like encouraging news for anyone hoping it was true. The second half took until 1963, and it came from a young American mathematician named Paul Cohen, who was not a set theorist by training, and who took up the problem partly because it was the most famous one available. He invented a technique now called forcing, and it is one of the genuinely new ideas of 20th century mathematics. Roughly, and with apologies for how much this leaves out, forcing lets you start with a model of set theory and carefully add new sets to it, controlling exactly what the enlarged model will and will not believe without breaking any of the axioms along the way. Using it, Cohen built a universe of sets in which all the standard axioms hold and the continuum hypothesis is false. There are sizes in the gap. Put the two halves together. Gödel showed the axioms cannot disprove it. Cohen showed the axioms cannot prove it, which means the standard foundations of mathematics, the ones everything else is built on, do not settle the question at all. They are silent. Both answers are consistent with everything we have agreed to assume. This is called independence, and it is worth being precise about what it does and does not mean. It does not mean the question is meaningless. It does not mean mathematicians gave up, or that the answer is whatever you want it to be. It means that the axioms we chose, back when set theory was being made rigorous, simply do not contain enough information to decide it. They are like a set of rules for chess that never says how many squares the board has. Perfectly usable and quietly incomplete on this one point. Let your thoughts go loose. Here. Nothing in this is going to be settled tonight by you or by anyone. Cohen received the Fields Medal in 1966 for the work, and it remains the only Fields Medal awarded for a result in mathematical logic. What happened next is the part that gets left out of the popular telling, and it is the more hopeful part. Mathematicians did not shrug and walk away. If the current axioms are silent, the natural response is to ask whether there are further axioms, ones we ought to have adopted, that would speak. That program has been running ever since. It involves what are called large cardinal axioms, statements asserting the existence of infinities so enormous that their existence cannot be proved from the standard rules, each one sitting above the last on a tower far beyond anything we described earlier tonight. These axioms have turned out to be remarkably well behaved. They line up in a clean order of strength. They settle many other questions that were previously open, and they have a coherence that suggests they are describing something rather than being invented arbitrarily. They do not settle the continuum hypothesis. That has been shown too, but other candidate principles have been proposed that do, and there is a serious and ongoing disagreement among specialists about which of them, if any, we have good reason to believe. Some hold that the hypothesis is definitely false and that the right axioms will eventually show it. Some hold that there is no fact of the matter, that the word set is simply not sharp enough to decide, and that we have been asking a question the concept cannot bear. Some are waiting. More than 120 years after Hilbert put it first on his list, it is genuinely open, and it is open in a deeper way than he could have imagined, since he expected an answer rather than a demonstration. that the question outruns its own foundations. Cantor died in 1918 without knowing any of this. He never learned that the thing he had chased for 30 years could not have been caught with the tools he had, that the failure was not his. There is a kind of comfort in a question like that. It has been sitting quietly for well over a century, and everything else in mathematics carries on beautifully around it, entirely undisturbed. Some things do not need to be resolved to be lived with. That one will keep. Let it. Chapter 10. We have been climbing all night. Let us go the other way for a while, down toward the small end, where the trouble is older and the story is warmer. Somewhere in the 17th century, two men working separately built the most useful piece of mathematics ever made. And neither of them could explain why it worked. Isaac Newton in England called his version fluxions and used it to describe how quantities flow and change. Gottfried Wilhelm Leibniz in Germany called his version the calculus of differences and gave it the notation we still use. Between them, they produced a method for finding the exact slope of a curve, the exact area under one, the speed of a falling body at a single instant, the path of a planet. The method gave right answers everywhere anyone checked. Bridges eventually stood up because of it, and comets were predicted with it. And the reasoning inside it was, by any strict reading, incoherent. Watch what happens when you find the slope of a curve at a point. You take your point, and you take a second point a small distance away, and you work out the slope of the straight line joining them. That is easy and honest. Then you make the small distance smaller and smaller to get a better approximation of the slope at the single point. At some stage in the calculation, you divide by that small distance, which you are only allowed to do if it is not 0, since dividing by 0 is not a thing you may do. Then, a line or two later, having got what you wanted, you throw the small distance away. You set it to nothing. It vanishes from the answer. So it was not 0 when you needed to divide by it, and it was 0 when you wanted it gone. Gamte, quantity, both ways. In the space of one calculation, Newton and Leibniz both knew this was the weak point. They circled it, described the small quantities as vanishing, or as evanescent, or as ultimate ratios of quantities in the act of disappearing. There had been earlier attempts in the same spirit, including Bonaventura Cavalieri's method of indivisibles in the 1630s, which treated an area as though built of infinitely many lines. Everyone could feel that something real was being described. Nobody could say what. The clearest attack came in 1734 from a philosopher and clergyman named George Berkeley, later the Bishop of Cloyne. In a short book called The Analyst, his argument was partly a jab. He was annoyed at mathematicians who dismissed religious belief as unfounded while resting their own subject on quantities that appeared and disappeared, as convenience required, and he wanted to point out the double standard. But the mathematical criticism was correct, and he made it precisely. He asked what these vanishing increments actually are. They are not finite quantities, since we discard them. They are not nothing, since we divided by them. He called them the ghosts of departed quantities, and the phrase stuck because it was fair. nobody had a good answer for about 100 years. Mathematics simply carried on using the method because it worked and quietly hoped, let your breath slow here. The repair took a century and a half, and none of it needs you awake. The fix arrived in stages, and it worked by removing the infinitely small from the argument altogether. Augustin Louis Cauchy, teaching in Paris in the 1820s, began recasting everything in terms of limits, replacing the vanishing quantity with a statement about approach. Then Karl Weierstrass, lecturing in Berlin in the 1850s and 60s, made it completely airtight, and the form he gave it is what students learn today. The idea is to stop talking about a quantity that is infinitely small and instead make a promise about closeness. To say a slope equals some value no longer means that you divided by something infinitesimal. It means this: name any tolerance you like, however tight. Ask that the computed slope come within that tolerance of the value. There is always a small enough distance that guarantees it, and once you are inside that distance, it stays true. There are no ghosts in that, and nothing appears or vanishes. Every quantity in the argument is an ordinary finite number, and the endlessness lives entirely in the phrase name any tolerance you like, which is Aristotle's potential infinity, allowed all along. That is what a limit is. It is a promise that can always be kept, and it is the machinery under every derivative and every integral ever computed. So, the infinitely small was banished respectably, and mathematics became rigorous, and everyone agreed the ghosts had been laid to rest. Then in 1960, a mathematician named Abraham Robinson brought them back. Robinson had been a fighter pilot's aerodynamicist during the war and came to logic afterwards. Using tools from mathematical logic that did not exist in Berkeley's time, he built an extended number system containing all the ordinary numbers plus new ones, including numbers greater than 0 and smaller than 1/2, smaller than 1/100th, smaller than every ordinary positive number you can name, and yet not 0. These are genuine infinitesimals, fully rigorous, with infinitely large numbers at the other end as their reciprocals. And in that system, the original arguments of Newton and Leibniz work almost exactly as written. You take an infinitesimal step, you divide by it legitimately because it is genuinely not 0. And at the end, you take the ordinary number nearest to your result, which is a defined and legal operation rather than a sleight of hand. He published it as non-standard analysis in 1966. Everything provable with it is provable without it, so nothing new became true. What changed is the standing of the old intuition. For 200 years, the story taught to students was that Newton and Leibniz had been working with a confused idea that had to be replaced by something better. Robinson showed that the idea was not confused. It was just ahead of the equipment needed to state it safely. The ban had been about what could be proved, not about what was real. There is a lesson in there about being patient with people who are right without being able to show it. You can hold both pictures now, a slope as a promise about closeness, or a slope as a ratio of quantities, too small to measure. They agree everywhere. Choose whichever one lets you sleep. The curve is smooth, the tangent rests against it at exactly 1 point, and it has been doing that quietly for as long as the curve has existed. Chapter 11. Here is the confusion that causes more trouble than all the rest of them put together, and it can be cleared away in one calm stretch. Infinity is not a number, not a very large number, not the biggest number, not a number at all, in the sense that 3 is a number, and so is -7, and so is the square root of 2. It does not live on the number line. It cannot be added to your bank balance. And every strange result you have ever heard about it comes from someone treating it as though it could. Start with the case everyone meets first. What is 1 divided by 0? A great many people will tell you it is infinity. It is not, and the way to see why is to approach 0 slowly and watch what happens. Divide 1 by 1/2 and you get 2. By 1/10, 10. By 100th, 100. By 1,000,000th, 1,000,000. The smaller the bottom, the larger the answer, growing without any ceiling. So far the popular answer looks reasonable. Now come at 0 from the other side. Divide 1 by -1/2 and you get -2. By -1/10 -10. By -1,000,000th -1,000,000. The answers plunge downward without any floor. 2 approaches to the same point, 1 soaring, 1 falling, and they never come near each other. There is no single value sitting at 0 that both journeys are heading toward. So there is nothing to write down. There is a second way to see it, and it is even simpler. Division is the undoing of multiplication. To say that 1 divided by 0 equals some quantity is to say that this quantity multiplied by 0 gives back 1. But anything multiplied by 0 is 0. No candidates survives, so there is no answer, and calling the answer infinity does not create one. What people are reaching for when they say it is a real and useful statement. As the bottom gets closer to 0 from above, the result grows beyond any bound you care to name. That sentence is true and precise, and notice that it never claims anything is equal to infinity. It describes a behavior rather than naming a destination. That is what mathematicians mean when they write that something tends to infinity. Not that it arrives somewhere, only that it eventually passes every number you could name and stays past it. Infinity, used this way, is a description of a trend. People have been circling this for a long time. In 628, the Indian mathematician Brahmagupta wrote down rules for arithmetic with 0. The first anyone had attempted, and he did not get the division rules right, saying that 0 divided by 0 is 0. About 5 centuries later, another Indian mathematician, Bhaskara II, suggested that a quantity divided by 0 is an infinite quantity that does not change when things are added to it, which is closer to the modern spirit, though still not something the arithmetic supports. It took a very long time to arrive at the current answer, which is simply to leave that particular slot empty, ret here for a while. This part is a clearing rather than a climb. Once you see infinity as a description rather than a quantity, several other puzzles dissolve at once. Consider infinity minus infinity. It sounds as though it ought to be 0, since anything minus itself is 0. It is not 0, and it is not anything else either, because the expression does not mean what it looks like. It means take two quantities, both growing without bound, and subtract one from the other. If one is always exactly 5 larger than the other, the difference stays at 5 forever. If one is always double the other, the difference itself grows without bound. If they leapfrog each other, the difference never settles anywhere. 3 different situations, all describable as one endless thing minus another, giving 3 different outcomes. So, the expression carries no information. Mathematicians call such a thing indeterminate, meaning that knowing both parts grow without bound tells you nothing whatsoever about the result. The same goes for one endless quantity divided by another, and for a few other combinations of the same kind. They are not forbidden, and they are not paradoxes. They are questions with the details missing. Now, having said all that, here is the honest complication, and it is a pleasant one. You are permitted to add infinity to a system as an object, provided you say exactly what it is allowed to do. Mathematicians do this routinely. There is a version of the number line with 2 extra points bolted on at either end, one called positive infinity and one negative, and a full set of rules governing them. Any ordinary number plus positive infinity gives positive infinity. Any positive number multiplied by it gives it back. And the combinations that carry no information, such as one endless quantity minus another, are simply left undefined on purpose forever. That system is used every day and nothing breaks. Because the rules were written by people who knew which slots to leave empty. There is an even prettier version. Instead of 2 ends, add a single point at infinity and join the 2 ends of the line together into a loop. In that system, 1 divided by 0 is defined, and it equals that point. And the arithmetic works, because the soaring and the plunging now meet at the same place from opposite directions. This is not a dodge. It is the foundation of a whole area of geometry, and it began with the painters. When Filippo Brunelleschi demonstrated linear perspective in Florence around 1413, and painters after him began constructing pictures. Around a vanishing point, they were putting a point at infinity onto a canvas. Parallel lines in a painting meet on the horizon. In the world, they never meet. On the canvas, they must. And the place where they meet is exactly where a point infinitely far away would appear. In 1639, a French architect and mathematician named Girard Desargues took that seriously and built a geometry in which parallel lines genuinely do meet at a point added for the purpose. In that geometry, every pair of lines meets, without exception, and the awkward special case of parallels disappears entirely. His work was largely ignored for 2 centuries and then became a whole field. So the rule for the whole subject is this: you may not treat infinity as a number that was already there. You may introduce it as a location and give it laws, and then it behaves. The difference between those 2 things is the difference between an error and a piece of mathematics. Nothing is broken tonight. The line runs on in both directions, or it closes into a loop, whichever suits the work, and either way, it is perfectly calm about it. Chapter 12. Now the strangest result of the night, and it is strange in a way that turns out to be gentle once you see what it is actually saying. The claim, stated baldly, is that you can take a solid ball, cut it into a small number of pieces, move those pieces around by nothing more than sliding and turning them, and reassemble them into two solid balls, each exactly the same size as the one you started with. Not two smaller balls, and not two hollow ones, but two identical copies of the original. That is a theorem proved in 1924 by two Polish mathematicians named Stefan Banach and Alfred Tarski, and it is entirely correct. It also does not mean what it sounds like, and the difference between those two facts is where all the interest lies. Let us build up to it properly, because the ingredients matter more than the conclusion. It begins with a rule so mild that it took mathematicians years to notice it was a rule at all. In 1904, Ernst Zermelo was working on a foundational question about ordering, and in the course of it he made an assumption explicit. Given any collection of non-empty boxes, however many of them there are, you can choose one item from each box and gather your choices together into a new collection. Read that again, and it sounds like nothing. Of course you can pick something from every box. What could possibly be objectionable? For finitely many boxes, nothing at all, and you do not need an axiom for it. For endlessly many boxes, it depends on whether you have a rule for choosing. If you have infinitely many pairs of shoes, you can specify a choice easily by always taking the left one. That instruction covers every pair at once, however many there are. But if you have infinitely many pairs of socks, identical within each pair, there is no rule to state. You need to make endlessly many arbitrary picks with nothing to guide any of them, and to assert that the resulting collection exists. That assertion is the axiom of choice. It cannot be derived from the other rules of set theory, and it cannot be refuted by them either, which Kurt Gödel and Paul Cohen established with the same techniques they used on the continuum hypothesis. Mathematicians adopted it because a great deal of ordinary mathematics quietly depends on it. Without it, various perfectly reasonable statements about vector spaces and about products of collections stop being provable, and with it, you get the ball. Here is roughly how, in outline, with the machinery left in its box. Using the axiom of choice, you can carve a solid ball into pieces that are not shapes in any recognizable sense. They are not chunks. They are not slices. Each one is an intricate cloud of individual points, scattered through the ball in an infinitely fine dust, with no smooth surface anywhere and no interior. These clouds have a specific property, and it is the whole trick. They have no volume, not zero volume. No volume. The question of how much space one of them occupies has no answer, in the same way that the question of what 1 divided by 0 equals has no answer. They are called unmeasurable, and their existence had been known since Giuseppe Vitali constructed the first example in 1905, again using the axiom of choice. Once you have pieces with no volume, the obvious objection to the theorem evaporates. Ordinarily, cutting something into parts and reassembling them cannot change the total volume, because the parts have volumes and volumes add up. Here they do not, because there is nothing to add. The bookkeeping that would have caught the contradiction simply does not exist for these objects. So, two balls come out. Nothing is created, because volume was never a property of the pieces in transit. Felix Hausdorff had found the essential idea a decade earlier, in 1914, in a slightly different form, and Banach and Tarski sharpened it into the version people remember. Later work showed that 5 pieces are enough. Let this be a curiosity rather than a worry, and doze straight through it if you would rather. Nothing you own is at risk, because here is the honest part, and it deserves to be said plainly. You cannot do this with an orange. A real orange is made of atoms, a large but finite number of them, and any physical cutting produces pieces with actual volumes made of actual matter. The pieces in the theorem are not physically realizable, not with any tool, not in principle. They cannot be described, drawn, or specified. The axiom of choice guarantees they exist without ever telling you what they look like, which is precisely the sort of existence that Leopold Kronecker objected to earlier tonight. So, what is the result really telling us? It is telling us something about the relationship between infinity and measurement. A solid ball contains infinitely many points, more than countably many, uncountably many. Once you are permitted to rearrange that many points individually, with no obligation for the groupings, to have any volume, the intuition that quantity of stuff is conserved has nothing to stand on. Volume is a property of well-behaved regions, and the theorem produces regions that are not well-behaved. There is a lovely detail confirming this reading. The trick does not work in 2 dimensions. You cannot take a disk in the plane and slide and turn pieces of it into 2 disks. The reason is a subtle fact about the available rotations. In 3 dimensions, rotations about different axes can be combined in endlessly many genuinely different ways, and that richness is exactly what the construction feeds on. In the plane, there is not enough freedom, and area survives. So the paradox is not a flaw in mathematics, and it is not a hidden truth about matter. It is a report from the boundary of where the idea of size still applies. Some mathematicians did want to throw out the axiom of choice over this. Very few did, in the end, because the alternative universe you get without it is stranger and more inconvenient than the ball. There is a well-known joke among mathematicians that the axiom of choice is obviously true, the well-ordering principle obviously false, and nobody has any intuition about the third statement that turns out to be equivalent to both. That joke is the whole subject in one sentence. Our intuitions about the infinite were built by handling finite things, and they are not reliable out here, and the honest response is to choose your rules carefully and then follow them wherever they lead. The ball on the table is still one ball. It always was. Nothing in this room has been divided or doubled, and everything is exactly where you left it. Chapter 13. Everything so far has been mathematics, which is to say, everything so far has been about ideas that behave exactly as we define them to behave. Now the harder question. Is anything out there actually infinite? Start with the sky, since that is where people always start. When you look up, you are not seeing the universe. You are seeing a sphere around yourself, bounded by how far light has had time to travel since the universe became transparent. That boundary is called the observable universe, and its edge is currently about 46 billion light-years away in every direction. It is important to understand what that edge is. It is not a wall, and it is not the end of anything. It is a horizon, exactly like the horizon at sea. Standing on a beach, you can see perhaps 5 kilometers out, and the water does not stop there. You simply cannot see further from where you are standing. Someone on a ship at that distance has their own circle, extending past yours. Every galaxy out there has its own observable universe, centered on itself, extending beyond what we can see. Nothing about our horizon says anything at all about how far the whole thing goes. So how far does it go? We do not know. That is the honest answer, and it may stay the answer. What we can measure is the shape of space, and this is where it gets interesting. Space could in principle be curved, like the surface of an enormous sphere, in which case, traveling far enough in a straight line would eventually bring you back to where you began, and the universe would be finite while still having no edge, the way the surface of the earth is finite and has no edge. Measurements of the oldest light in the universe, the faint microwave glow left over from when the cosmos first cooled enough to become clear. Let us check for that curvature. Careful mapping, particularly by the Planck spacecraft, found space to be flat as far as anyone can measure, with any curvature so slight it is consistent with zero. Flat and unbounded is consistent with infinite. It is not proof of infinite. A very large sphere looks flat to anything standing on a small enough patch of it, which is why the ground outside your window looks flat to you. Our patch may simply be small, so the position is this. The universe is at least vastly larger than what we can see. It shows no sign of curving back on itself, and whether it goes on forever is not something current observation can settle. Some cosmologists think it likely infinite. Some think we should be cautious about asserting infinities we can never check. Both are reasonable, and neither is established. You may let this one go entirely. It has been unresolved for as long as there have been people to wonder about it, and it will keep until morning. There is strange consequence people enjoy, which deserves careful handling. If space really is infinite, and if matter is spread through it at roughly the density we see nearby, then somewhere out there, unimaginably far away, arrangements of matter would repeat, including, eventually, arrangements identical to this room. That argument is often stated with more confidence than it can bear. It leans on assumptions about how matter is distributed at scales nobody has observed and about the space of possible arrangements being limited. It is a serious idea that serious people discuss, and it is speculation, and it should be held loosely. Now the other place where infinity shows up in physics, and this one is less romantic and more instructive. Sometimes a physical theory produces an infinite answer. When that happens, the working assumption among physicists is not that nature has become infinite. It is that the theory has reached the edge of where it applies. The clearest case is the singularity. Take the equations of general relativity, which Albert Einstein published in 1915, and which describe gravity as the bending of space and time, and follow the collapse of a sufficiently massive star. Density rises without limit, space-time curvature rises without limit, and the equations produce infinities. The same thing happens if you run the expansion of the universe backwards to its earliest moment, Roger Penrose showed in 1965, and then with Stephen Hawking in the years following, that these singularities are not artifacts of assuming a tidy, symmetrical situation. Under broad and reasonable conditions, general relativity predicts them unavoidably. Penrose received a share of the Nobel Prize in Physics in 2020 for that work. The usual reading is not that infinite density exists somewhere. It is that general relativity, which says nothing about quantum mechanics, has been pushed into a regime where quantum effects must dominate, and it is reporting its own breakdown in the only way it can. The infinity is a signal, not a measurement. Something similar happened in the theory of light and electrons. When physicists first computed certain quantities in quantum field theory, the answers came out infinite. The technique developed to handle this, called renormalization, works beautifully, giving predictions that match experiment to more decimal places than almost anything else in science. Richard Feynman, who shared the Nobel Prize for that work in 1965, was nonetheless uncomfortable with the procedure for the rest of his life, describing it in a later book as a shell game and a dippy process, and saying he suspected it was not mathematically legitimate. Later understanding softened that discomfort considerably. By reinterpreting these theories as descriptions valid only up to some scale, with the infinities reflecting our willingness to pretend they hold at all scales. But Feynman's instinct was sound. An infinity in your equations is usually the equations telling you that you have asked about somewhere they cannot go. So we end this stretch with a modest conclusion. Infinity is unquestionably real as mathematics. Sizes of infinity, ladders of them, arrangements past the end of counting, all rigorous, all provable, all sitting there, whether anyone thinks about them or not. Whether infinity is real as a feature of the physical world is genuinely open, and where it appears in our best theories, it more often marks a limit of our description than a property of nature. That is a smaller answer than the question seemed to promise. It is also the true one. The sky outside is doing whatever it does, at whatever size it happens to be, and it has never once needed us to settle the matter. Chapter 14. So, what did all of this buy us? It is a fair question to end on, because from the outside this can look like the purest kind of abstraction. A group of people arguing about the sizes of things that do not exist while the world got on with its business. It is not, and the reason is sitting quietly under almost everything. Every time an engineer calculates the load a beam will carry, every time a pharmacist works out how a dose decays in the bloodstream, every time a weather model steps forward 6 hours, every time a spacecraft is put on a path to a planet that will not be there for 4 years. The mathematics underneath is calculus, and the thing that makes calculus mean anything is the limit. And the limit, as we saw, is a promise about endlessness. Name any tolerance, and I can get inside it and stay inside it. That is a statement about a process with no last step. 2,000 years of nervousness about the infinite, resolved into a form careful enough to build bridges on. The machine you are listening to this on is full of infinite series. Your device does not have a table of every sine and every logarithm stored away. It has a handful of endless sums, chopped off at the point where the remaining terms are smaller than the precision anyone needs. Every one of those calculations is a piece of Zeno's argument, handled correctly, and the deeper layer, the one about sizes, turned out to matter too. When mathematics was rebuilt on rigorous foundations in the early 20th century, sets became the material everything else was made from. Numbers are sets, functions are sets, spaces are sets. That whole enterprise begins with Cantors' decision to treat a completed infinite collection as an object you may hold and compare. The uncountability of the line explains why almost every number is one we can never write down or name. There are only countably many descriptions, because a description is a finite string of symbols, and those can be listed. There are uncountably many numbers, so the numbers we can specify are a vanishingly thin dust in the ocean of the rest. That has consequences in computing, since a program is also a finite string, and so the functions a computer could ever calculate are only a countable sliver of all the functions there are. Alan Turing's work on what machines can and cannot do rests on exactly that counting. Let all of it go now, if you like. The rest of this is a gathering up rather than anything new. Georg Cantor lived long enough to see the tide turn, though not comfortably. He spent his last years in Halle, in poor health through the food shortages of the war, and died in the sanatorium there in January 1918. He was 72. He had been ill on and off for more than 30 years. And the mathematical world that had once had a Berlin professor working against his papers had by then largely come to accept what he had done. In 1926, David Hilbert wrote that no one should be able to drive us out of the paradise that Cantor had created for us. It is the sentence most often quoted about all of this, and the word paradise is doing something specific. He did not mean it was pleasant. He meant it was a place, a real one, that had not existed before and that could now be lived in. So, let us walk back through the night slowly and then let it go. A man in a Greek colony noticed that crossing a room requires infinitely many steps, and nobody could say for 2,000 years why that was possible. The answer was that endless sums can settle, though only some of them, and the ones that settle must be handled with more care than ordinary arithmetic ever required. Aristotle drew a line between the process that never ends and the completed endless thing, and forbade the second, and that ruling held until Galileo. Galileo stood at the door, noticed that the squares both thin out to nothing and match the numbers exactly, and decided, reasonably, not to go through. Georg Cantor went through, by choosing pairing as the meaning of size, and a hotel with no last room found space for a guest, and then for infinitely many, and the fractions folded into a single list along a diagonal walk, and every solution of every equation folded in too. Then the diagonal argument on one page showing that the numbers on a short piece of line cannot be listed at all. More than one infinity. Then the ladder above it, with no top. Then the arrangements that continue past the end of counting. Then the question of what sits between the countable and the line, which Kurt Gödel and Paul Cohen proved cannot be answered by the rules we have. The infinitely small, banished by George Berkeley's honest complaint and by a century of careful repair, and then quietly restored by Abraham Robinson once the logic was strong enough to hold it. Infinity refused a place among the numbers, and then, given a place of its own with laws attached, the way the painters gave the horizon, a point where parallel lines could meet, a ball divided into clouds with no volume, and reassembled into two, teaching us that our sense of how much stuff there is stops applying where measurement does, and a sky that may or may not go on forever above a species that has not yet found a way to check. Which brings us back to where we started. Count in your head, again if you are still with me. 1, 2, 3, going out into the dark, cross out every odd one, and you have thrown away half of everything, and you have lost nothing at all. And now you know exactly why. Not because size stops meaning something out there, but because size means the one honest thing that can still be asked, which is whether two collections can be paired off with nothing left over. That was the whole discovery. Somebody stopped demanding that infinity behave like a large number, asked a smaller question instead, and the smaller question turned out to have an enormous amount to say. The numbers are still going. They were going before anyone counted them, and they will go on. After this room is quiet, without needing to be watched or finished or understood, there is no last one. There does not need to be. See me now. Good night.